Good afternoon, everybody. I hope you enjoyed your lunch, and welcome back. And we're going to shortly have our second plenary speaker. And Laurent will introduce our second plenary speaker, but before that, I'm just going to ask Ivan to give just a few housekeeping announcements.
Thanks, John. So, hi everyone. The thing about rooms and Zoom and so on, this is quite important. So in the majority of rooms now, we have the system when you just upload your slides on laptop, you go to Zoom, you click the button to share the screen, and they are live not only on the laptop, but they are live in the projection as well. So this is very important. If you are a chair of a session, you make sure that you share the slides, share the screen on Zoom. This is very important. Now, what's this? This. Sorry. You have microphones, maybe not like this, but some microphones in the rooms. Make sure that when people ask questions, they use microphones, because this is needed so that people on Zoom can hear what's happening. And there is only one room now, room 9, which has some technical difficulties. It has the system where you also need not just share the screen, but transfer the slides to the right side, which becomes your projection. But if you have any difficulties, there is a note with a number. You just dial this number or send me a message on WhatsApp and I will help, we will sort it out. Okay, thank you.
So good afternoon to all. So I'm Laurent Ferrara. I'm one of the IIF directors, and I'm going to chair this session. So we are super happy to welcome Johanna Ziegel. So Johanna is Associate Professor of Applied Stochastics at the University of Bern in Switzerland. And she's also visiting a scholar at the Heidelberg Institute for Theoretical Studies. So Johanna has a wonderful track record of great publication. She has been a council member of the Bernoulli Society and has served as associate editor for the Journal of Multivariate Analysis, Electronic Journal of Statistics, Statistics and Risk Modeling, and Mathematical Finance. And currently she's part of the editorial board of Bernoulli and the Journal of Applied Statistical Association. So, Johanna, we are very pleased to have you for the first time at the ISF, and we hope to rely on you to be part of our network in the future. So the floor is yours for about 50 minutes, and we will have time to take questions at the end of the presentation. Johanna, please.
Thank you very much, Laurent, for the kind introduction, and the organizers and the scientific committee to invite me here for this lecture. I will speak today about valid sequential inference on forecast performance, and the two papers that I will mainly touch upon are joint work with two of my PhD students, Alexander Hensi and Sebastian Arnold. Alexander has just recently graduated beginning of June, so now very highly deserved, holds his PhD degree. And Sebastian is still doing his thesis. So let me, does this work? No, it doesn't. Maybe put it here. I'll press once maybe. Yeah, no, we go. That's good. Oh, thank you. So let me jump right in. I want to tell you something about valid sequential inference, and I'll do that with two examples. And the first one is the one I'm introducing here. So the interest is here to compare probability forecast performance. So we have two forecasts, RT and QT, both are numbers in 0, 1, that are supposed to predict the event probability for a binary outcome. So our yt plus h is our prediction horizon, just takes values 0 or 1, and the rt or qt is the probability that our yt plus h is equal to 1. Okay? So as a leading example, you can think of the probability of rain h days ahead, just to have a working example that we can think about. So the classical approach to evaluate whether forecast RT or QT is better is that we take some proper scoring rule. And I've given here the definition of a proper scoring rule for a binary event. So such a proper scoring rule is a function that takes its input, our forecast, and the observation. And we want that if the true event probability of y is pi, then the expected score should be minimized when we forecast this pi amongst all possible probability forecasts that we could give. And two, of course, prominent and well-known examples are the Breyer score here, or the quadratic loss, and the logarithmic score that we have here. Now then we could be interested to draw inference to say that, okay, we really actually have a significantly better forecast QT than RT. Then, of course, we're considering some null hypothesis that I'm giving here. So here I'm giving a null hypothesis about conditional predictive performance concerning RT and QT. So my hypothesis is that RT has a conditional lower score than QT for all time points. Mathematically, just to give here also the background, we have FT is some filtration that it could be just a filtration of past forecasts and realizations, could contain more information that we use for forecasting. It's just essentially we have the information that we use for forecasting. And we assume that our sequence of forecasts and observations is adapted to that filtration. And then our null hypothesis is, of course, just a set of distributions such that this condition is fulfilled. So you can think of that intuitively, or here is a mathematical background. I was trying to address this very diverse audience, which I find a challenge, so I'm trying to give a bit more technical parts, but also try to keep intuition throughout. Okay, now what's commonly done is that we take the average realized scores, and we check which forecasting method has a smaller average realized score. And then we know in order to test our hypothesis, we can compute a p-value based on the statistic of average realized scores. We use some approximate normality result where, of course, we have to be a bit careful. How do we estimate the variance here? And we could have time dependence. But there's literature on this, and there's very good results on this. Is, of course, a classical Debord-Mariano test. And then there's a famous paper by Giacomini and White to have further push this theory under weaker assumption to get still asymptotic normality. So in principle, you see I still have a bunch of slides left, so this is not what I want to do, right? So I want to convince you that maybe, I'm not saying we shouldn't use score rules for forecast evaluation. I want to stick with the same null. I still want to evaluate the same null about predictive performance, but I want to challenge you to rethink a little bit about the testing part, about how we draw inference, which one's really significantly better. So why do we need another significance test for score differences? Often, and I think really this happens very often, even to statisticians who know the problem at heart, who are well-trained, who have really know they shouldn't be doing this, but it's just too tempting not to do it. We look at the data before the end of the sample. Before we have observed all data, we check already a little bit, is it going to be better or not? Then also, we have done our study, we have, after 2 years, concluded this is the better method. But then, of course, more data comes in, and a few years later, we look again, right? In order for our p-value that I gave before to be valid, we can't do that. We have to fix the sample size in advance, once and for all, and then we have to throw away all the data, and we start with a new problem. Now, the question is, of course we know we shouldn't be doing this, but is this really a problem? And I want to give you a small simulation study just to illustrate that this is in fact a problem that inflates the type 1 error substantially. So what we've simulated here is it's a simple setup. The simulation study is not complicated. It's not supposed to give you very deep insight. It's just supposed to have a working example where we see that we're not dealing with something that practically never matters. So we have an IID sequences of forecast RT-QT that we draw from a uniform. The true event probability is a mixture of RT and QT, and then we draw our realization one period ahead given this true, with this true event probability. Both forecasters here only have partial information. Neither one is calibrated, so this is not a matter of one being calibrated or not. And we use the Breyer score for comparison, so the squared error, and then we can explicitly compute, so our parameter here in this problem is the mu, this mixing parameter of how relevant is RT or QT to the true event probability. And when we use the Breyer score for comparison, you do a bit of calculus and you find out that our null is true if and only if this mixing parameter is less or equal to 1/2. Okay? And then we can look at the rejection rates. We have an IID sequence, so this is not a Diebold-Mariano test, it's just a good old student's t-test. There's nothing too fancy about this. So when you look at focus on the lowest line you have here in this graph, I said here the null is true as long as mu is less or equal to 0.5. Here you see rejection rates for a total, the sample size is always 600. We did many Monte Carlo application to get the rejection rates. And for the lines with the dots, you see everything's fine. We don't reject too often. Everything's good. We've done how we should apply the t-test. Now, the lines above, when you go one up to the triangles, that's the case where after 300 data points, you thought, oh, I'll have a look if I can already reject. Right? And then you see, of course, we don't keep our type 1 error anymore. We already violated. And it gets worse here. We are at 5 stops in between, and we are at 15%. If you start peaking every day, of course, this goes further up. Now, for this particular case, of course, there would be an easy fix. We have a maximal sample size that's 600. We want to stop 5 times. We do a Bonferroni correction. We're good again, right? No magic there. So I want to convince you that there is a better way of doing this than a Bonferroni correction where, again, we would have to specify the maximal sample size. We would have to specify how many times do we peak. And maybe we just peak one more time just because it's convenient, and then we get a better rejection. So can we design a theory? Can we use methods that allow us to peak every day without compromising type 1 error control? Yeah, so we can do this, and we get probability now for the specific case of the probability forecast for binary events. We can construct such forecast dominance tests. They are valid in finite samples. We also don't have an asymptotic test, but really a test that's valid in finite samples. We don't need any assumptions on the data generating process. They don't have to be stationary. They don't have to be IID. They just have to arrive sequentially. That's required, but I think that's natural in a forecasting context. And they're anytime valid. That is, we can stop as soon as we think we've gathered enough evidence. So how do we do this? I want to make a little bit of an excursion and give a bit of insight into the more general theory that's underlying this. So this is not specific to the null that I've presented, but I hope it gives you a good working example in your mind that you can follow me while we're doing this. But this applies much more generally. And this is also not exclusively our work. I'll mention some other groups who have recently pushed this area quite a bit. So we have some null hypothesis that concerns some adaptive process XT. And as I said here, you can think as an example of this process on forecast performance for binary events. Now, what is what I call a standard sequence of p-values? So this p-value that are computed from the student t-test. That would satisfy such an inequality. So for any fixed t, we know that we have type 1 error control. And that's not good enough because that doesn't say anything if this t here becomes random. So if we peak and reject as soon as we have seen something significant. So what we would want is a so-called anytime valid sequence of p-values, namely one where the probability that we ever see a p-value less or equal to alpha is controlled, which is, and this is not completely obvious that this is equivalent, means that for any stopping time, we control the type 1 error. So we are allowed to peak, we are allowed to stop as soon as we go below the level that we are aiming for. Now, if you talk about anytime or sequential inference, you should not forget to mention the grandfather of this. The grandfather of sequential testing is Abraham Wald with his sequential probability ratio test. This goes back to 1945. In fact, it was it's quite interesting to read the intro to his paper from 1945. He developed this before, namely during World War II, and it was classified as potentially too valuable to the enemy that he was not allowed to publish this before the end of the war. So this was really important statistical theory. So the assumption here, what is he testing? We have an IID sequence xt, and he tests a simple null that xt follows the law p0 against a simple alternative that xt follows p1. And we assume that p0 and p1 have densities f0 and f1. Then he fixes a test level alpha and a desired power 1 minus beta, and defines this cumulative product of likelihood ratios. And then he shows that we get a valid testing procedure if this cumulative product of likelihood ratios exceeds 1 minus beta over alpha, we can accept the alternative. And if it goes below beta over 1 minus alpha, we can accept the null. And as long as we're in between those bounds, we continue sampling. And the big sales point for Walt was a little bit different to what I think is relevant in forecasting, in the sense that he designed this test in order to be able to collect as little samples as possible in order to draw a conclusion. So at the time, it was costly to make the experiment and to recruit one more sample, which is of course not the case that we have in forecasting. We have the forecasts coming in anyway, and we want to monitor them. So I think conceptually there's quite a difference, but nevertheless, this is I wanted to give this just to give a bit of historical background where this started and where this came from. One observation here, and I'll come back to this. This MT that we construct here is a non-negative martingale under H0. And these martingales are quite important for the sequential testing, but I'll get back to this just as a comment already. As I said, there's been a recent surge of interest in tons of generalizations of Walt's sequential probability ratio test to composite nulls and alternatives, highly composite ones, non-parametric ones. The tools there are so-called test supermartingales, e-values, e-processes. I give the definition in a moment. I just want to alert you to this. This here is a screenshot from a recent conference that finally happened after 2 COVID cancellations. On this topic, I'm giving you here the website of this mainly, should you be interested, at this conference, a really nice reading list that's a very good starting point for this topic was compiled, so I thought this might be of interest and a good starting point should you think this could be relevant for your work. So, what is underlying the idea that this community has pushed recently? And that's to interpret testing slightly differently, namely to take a betting interpretation of testing. So suppose we have our null, that would be with the probability forecasts, the null that RT has better predictive performance than QT. How can we find evidence against that null? If we believe that it's false, right? We believe the opposite. Well, we try to win money by betting against it. We start with some capital at time t, and then we invest our capital and we make a bet. This ET is our bet here. This bet is non-negative. It depends on the future outcome. And we have to design it such it's an acceptable bet if, should the null hypothesis be true, we cannot make any money, right? In expectation, on average, we will not make any money because our payout is the capital times the bet we made. Should the alternative be true, we're hoping to design our bet such that we make a lot of money. We multiply our capital by a lot. Now, we get the resulting capital process here, and here the definition comes on the next slide. This capital process is then a test supermartingale for our null. Now, here we see for the first time this bet here is what we call an e-value. It's a non-negative random variable that has expectation less or equal to 1 under the null. So it's not such a complicated object. Non-negative random variable expectation less or equal to 1 under the null. And a very nice introduction to this betting interpretation of testing is given by Glenn Schaefer in a JRSSA discussion paper. He calls, just that there's no confusion, he prefers to call these E's betting scores, but the rest of the community calls them E-values. Yeah, so what is a test supermartingale? This is now just the abstract formulation, what I said before. It's a non-negative adapted process that starts at 1, such that for any probability measure under the null, we have that the expectation, the conditional expectation of mt plus 1 given if t is less or equal to mt. And now here comes in some theory from probability theory from the PhD thesis of Ville. He showed that these such test supermartingales are exactly the ones that we want for valid sequential inference, because if we take 1 over such a test supermartingale, we get exactly an anytime valid p-value. This is exactly the definition I had given. If you here take this 1 over mt as the p-value, you see that the probability that we ever go below the level alpha is bounded by our level. So we get our anytime validity. And one example is, of course, this likelihood ratio process of Wald. Now, this looks maybe abstract if you don't work every day with martingales, but constructing these test martingales is actually not that difficult. And I want to convince you that they are actually quite intuitive to construct and walk you through the construction that we have done for the forecasts for binary events. So as I said, an e-value is just a non-negative random variable that has expectation less or equal to 1 under the null. And you see that in some sense, an e-value is much simpler to define than a p-value. You think of what is a p-value, that's a random variable with values in 0, 1 that's stochastically smaller than a uniform distribution. So you need to know something about the entire distribution of that random variable. For the e-value, you only need to know its mean and that it's non-negative. That is considerably simpler. Now, if we have an adapted sequence of conditional e-values, there you just, what that means is that you can only use the information you have at the time of forecasting to construct your e-value. Then you always end up with a test supermartingale and you get your anytime valid inference that you would like. Now, of course, if you want to play the devil's advocate, there's a very trivial and simple choice how you can construct an e-value. You just say, I take constant 1, right? You never gain any evidence, but you're perfectly valid, it's no problem, right? That's not what you want to do. You want to find evidence against your null. You don't want to be idle and just look at your process. That's always 1. So how can we ensure that our test also has power against alternatives? So we somehow want it to grow fast if the null is wrong, right? We want our test martingale to give us lots of money if the null is false. So has been a bit of debate what criterion to maximize for e-values. And the current consensus is that we should maximize the expected logarithm of our test supermartingale for any distribution in the alternative. What is one, I think, compelling motivation for this criterion is the following. Suppose we have a test supermartingale that's given as such a product, and our e-values here are IID, such that the expected logarithm is bounded below by some number L. Then by the law of large numbers, we get that our test martingale then grows exponentially with where the growth rate is exactly this lower bound L. So what that means is if we maximize this expected logarithm, we maximize the growth rate of the capital process. You can think, of course, of other criteria to maximize here. In the literature, there's several arguments why the logarithm is the best idea here, but in some applications, this could be different. What you should be aware of is you're not necessarily maximizing the power of your test in the terms of the 1 minus the type 2 error. This is not the same thing. Maximizing this log criterion is not the same thing as maximizing the power. Why is maximizing the power not a good idea? It turns out, and this is nicely illustrated in the paper by Glenn Schaefer that I said, if you you can go for a criterion that maximizes power. But in terms of interpreting that as a bet, that means that with positive probability, you allow for bets where you lose all your capital in the next round. Okay? So if you maximize with respect to power, you're very prone to just losing everything. If you would do that with your own money, you would never do that. That's why I think the different criteria than just power of the test are the better thing to do here. Yes, as I said, we maximize the capital that we can make under the alternative. And in practice, of course, this criterion doesn't lend itself very well to really practically derive a test, but it's kind of the theoretical backbone that we try to imitate then empirically to get good test martingales. Okay, so back to now our probability forecasts for binary events. Here's again the null hypothesis that we're interested in. I want to say a little bit, there are at least two interesting extensions that you can easily accommodate in this framework. One is, it's very easy and already built into the framework that you can test forecast dominance under an adapted condition. For example, you can say, I only want to test for forecast dominance in summer month. You have no problem. We don't make any assumptions on the data generating process, so this can be non-stationary, this can just occur occasionally. The only thing that's important is you have to know your condition at the time of forecasting. It cannot depend on the outcome. That's not possible. Okay, then there is also a stronger hypothesis that we could test that is that we want forecast dominance under all possible proper scoring rules for binary events. Becomes a very small hypothesis, a very strong criterion, but it's possible to do that. One could also be interested in a weaker hypothesis where we say we want to test whether the average conditional error is less or equal to 0 for all t. That's also possible. This is not work by us, but by YJ Cho and Aditya Ramdas. Just to give you an idea, there have already been some extensions in several directions. Now, how do we construct now our test martingale? We go back to one step back, that's slightly simpler. We just look at one forecast period. We have deterministic numbers are in Q and 0, 1. We have our outcome Y, that's binary, and we want to see if this thing holds here. So if the expected score of R is less than the one of Q. So our null hypothesis then just becomes a part of the interval from 0, 1. And for a given score, we can compute that it's always such an interval depending on which one's larger or smaller. This is an explicit formula. It depends on the scoring rule. And here are the two most relevant ones. So for the Breyer score, it's just the midpoint between R and Q that separates the null from the alternative. And it's a slightly different formula for the logarithmic score. But that's all explicit. We can just compute that. And now we get the following characterization of all possible e-values that we can construct for this null. And here, I want you to mainly look at the structure of these things. So the first important thing to note is we can construct an e-value. So we can construct a valid test for sample size 1. Well, it's not going to have a lot of power, but I'm giving you a valid e-value for sample size 1, which means 1 over the e-value is a valid p-value. So we have already that I find kind of amazing that we can, with sample size 1, we can construct something that gives us a valid test. The structure here is the following. Here you see is the score difference. The thing on the bottom, Timo told me that I should say this because this is apparently confusing when you see this for the first time. This has nothing to do with variance like it's usually for test statistic. That's just simply the maximal absolute difference that can occur for this score difference. And the only reason we need this here is we have to make sure that our e-value here is non-negative. So when we have our parameter lambda that allows us to tune our e-value, the whole thing can never be negative. So we have to make sure that we know the bounds of this quotient. Okay, so you see what's left here is one tuning parameter, one lambda between 0 and 1, that gives us all possibilities for e-values for this null. Now coming back to our log criterion here, we can now optimize for any pi, so for any possible event probability in the alternative, we can maximize this expected log E value in lambda. And it turns out that we get something that is a likelihood ratio. Well, here we have the probability, this pi in the alternative, and down here we have a kappa, and this kappa again is just something that depends on the chosen scoring rule. Explicit formulae for it, there's nothing unknown. Now, how do we get from lag 1 to higher lags? What we do is simply by taking products. That's, as I said before, now we have conditional e-values, we just multiply them up. Each e-value is evidence against the null in one time step, and since we're doing this continuous betting, we multiply the capital we gain. Yeah, and then we have our test supermartingale that works, that we can use now for these sequential tests for the binary predictions. As said, we have no assumptions, no stationarity that I assumed anywhere. We get this. We can do it for higher lags. Don't want to go into too much detail here. There is a little bit of tricks involved for higher lags. It all works. It's in detail in the paper. I think it's more confusing than helpful to go into it. But it's not that we don't treat it. We really have it. It works out. The combination formula is a little bit more complicated, and you get a slightly weaker result here, so you have to be a bit careful which stopping times you use, but it works. So now we still have one thing left, and this is these parameters lambda t. That we can use this, the lambda t depends how we bet. So we have all our information until today. We want to bet our e-value for tomorrow, and the lambda t can depend on everything we know today to issue our bet for tomorrow. We will always get a valid e-value as long as it's between 0 and 1. And now validity is then guaranteed for all these choices. However, power requires that we choose this lambda t in a good way. Now, we take inspiration from the 1 period setting where I told you we can optimize for this lambda, and then we get this likelihood ratio formulation. So here, what's really the tuning parameter now instead of lambda is this pi. So that's our best bet for the true event probability under the alternative. And that's quite interpretable. We put as pi, we put the event probability that we deem most likely. That's what we put our money on the alternative that we think that's most likely. And if we use here the Breyer score for simplicity, if we're very confident that Q, sorry, this should be an R, not a P. If we're very confident that Q is really the true event probability, then we will put all our money on Q. If we think, yeah, Q is better than Q is better than R, but I'm sorry, I have a typo here. These should be R's, not P's. If we think that Q is better than R, but there's still some information also in the forecast that's worse, then we can go here for some combination of the two for our guess of what we put our money on. We don't have to put everything on Q. Now, in order to improve power of the tests that we get, we can stop. That's allowed. We can stop as soon as we see significance. For lag 1, we have here a very simple rule to stop. As soon as our process goes above 1 over alpha, we stop. If we have greater lags, then it does get a bit more complicated, but it's all doable, it's all implemented. I'm coming back to the simulation example that I introduced in the beginning, and I just want to show you how these different betting strategies affect what we get for power for these tests. So either here we're very confident that the method we want to show is better is actually the truth. Then we bet on it. Here, for this one, an oracle is necessary. Here we bet on the correct event probability. Of course, we cannot do this in practice because we don't know it, but to see in the numerics what we can hope for, what's the best option, we included it. And here we have some mixture of RT and QT, so we say we're somehow in between what we believe. Now here, let me walk you through what we have here. This is the graphic you've already seen, that the power deteriorates if we do optional stopping with the t-test. Here now you see what effect on the power it has if you use this test supermartingales or these e-values, if you do optional stopping or not. So this is the same betting strategy The lower one is if you don't do optional stopping, so you wait until the end of the 600, and then you look at your e-value at the end, and you, depending on that, you reject or not. If you stop as soon as you see an exceedance over 1 over alpha, you get a higher power. You see you don't violate the level. You keep the type 1 error control, but you do get better power. And that's both strategies are valid. It just depends on what you're after. And here you see different possible betting strategies. Here the oracle betting strategy is actually the dotted one. Now this is the oracle betting strategy, and you see here, and this is not an arrow, you see here that some betting strategies have better power than the oracle. And that's exactly an illustration of the fact that I said before. This log criterion doesn't maximize power, it maximizes growth. And what we plot here is power. So this crossing is really not a mistake. That is inherent in the theory that can be explained. Here you see a bit of a comparison how much in power you lose in comparison to a correctly applied student's t-test. Yeah, you do lose some power. We have to pay some price for the anytime validity. This part. But I want to convince you in the data application that we don't only lose power, but we also gain something. Not only do we gain that we can do optional stopping, but we gain something else. Now let me illustrate this in a data example. We looked at predictions for the probability of rain based on the ECMWF ensemble forecasts at 4 airports. So we have airport station observations, and we're comparing 2 different post-processing methods. So we take the raw ensemble forecast from the ECMWF ensemble, so we have numerical weather prediction forecasts that come out of the numerical weather prediction models. The ECMWF ensemble has 51 members. And then there's these ensembles are known to be, have dispersion errors and biases that are systematic, and they can be improved if we do statistical post-processing. So we use the numerical weather prediction output as a covariate, and with training data, we try to correct for these bias and spread errors in order to get better predictions for, in this case, the probability of rain. I don't want to go into detail about which post-processing methods we compare here, but just that you have a feeling for why one hypothesis should be true or not. So this HCLR is a parametric post-processing method that's specifically tailored for precipitation. That's fine-tuned to do well for precipitation predictions. And we compare it to a generic method, IDR, isotonic distributional regression, that's out of the box without any tuning parameters, works for any real valued outcome, discrete, continuous, mixed discrete, continuous. But it's really, no tuning has been done. This is not specific to precipitation. It's non-parametric. So let's look just at the first hypothesis. So the hypothesis is that this HCLR, so the targeted parametric method specific for precipitation, should outperform the generic method, IDR. Okay? And the null is, of course, that the IDR achieves a lower Breyer score than HCLR. That's what we want to reject. Now, here you see now a comparison. We don't have to look at the numbers in detail. The main message is this is a comparison of e-values and p-values that you get from a Debord-Mariano test for the same problem. What's the main message is you get roughly the same conclusions. Now, that wouldn't be very interesting in itself. Then we would say, like, well, as long as I'm honest and I don't do optional stopping, I can just stay with whatever I did before. So let me try to convince you that there is more info that you get from the e-values besides the fact that now you are allowed to peek at your data. So these are here, these capital processes, these test supermartingales, these e-values, whatever you want to call them, that you observe over time. Here this is lag 1 for Brussels, the dots, and then the other airports are different things. And at each day, you see whether you accumulate evidence against the null or you don't. So here, in this case, for HCLR against IDR, in my mind, surprisingly, at lag 1, the specific method, we cannot find evidence that it does a better job than the generic method. Right? But it's also a result in itself. At higher lags, we do find evidence. But here you see, like, we don't accumulate any evidence. We stay very low. Here, This one here is interesting. There we compare HCLR to a simplified variant of HCLR, so different model structure, but a bit less parameters. And there you see nicely how it goes if you want to, if one model is really clearly better than the other, you see how over time, at different speeds, you accumulate evidence against your null. Your capital grows quite steadily. And for the triangles, so that would be Frankfurt, you can actually reject before you've seen half the data already that the other method is better. And you're allowed to do so. You can do that way before the end of the data. And for some others, you have to wait a bit longer. Okay? And for the lowest one, you can get to the end and say, okay, so far I haven't had evidence, but you are allowed to just continue your study. There's nothing that theoretically speaks against just going on. Okay, now you say binary predictions is not all we have. There's several extensions. Ongoing work is for probabilistic forecasts. It's also possible for quantile forecasts and so forth. But that's work in progress. What I want to tell you now, because I also said we can monitor calibration. So this is the last point I'll get to. I'll do this quite intuitively because I think there you even see this monitoring aspect a bit better. So what I mean by calibration here, I should of course specify that because now we're dealing with predictions for a real valued outcome, probabilistic predictions. So we have a full predictive CDF for real valued outcome. And what we're interested here is in probability integral transforms. So is the pit histogram flat, yes or no? We have calibration in that sense. So this is the specific notion of calibration we're targeting. One could look at other notions of calibration for real valued predictions, but for the moment, this is the one we've looked at. Of course, rank histograms also fall in this category. And if the predictive CDFs are not continuous, the natural adaptations, that can all be done. So the null hypothesis of interest here is that the distribution of our PIT, given the past PIT values, is uniform. That's the null we want to test. And one can construct such sequentially valid tests based on test martingales. Now, why do I say that this is interesting and gives you more information than just looking at the pit histogram? We have here, again, weather forecast data for precipitation, temperature, and wind speed, also based on an EMOS post-processed ECMWF ensemble at weather stations in Germany. So this here is Helgoland. And I want you to focus here on the 24-hour temperature forecast. So we are here in this pit histogram. You see here, it's not calibrated, it's not flat. Yeah? You can probably also, with the usual, you can reject that this is flat. But then you just know it's not calibrated. Now, can we get more information if we look at our test martingale over time? So this is what's plotted here in the same way. You see here, you have a very interesting pattern. And what this means is, in the parts where it goes up, you gain evidence against calibration. And then you gain evidence against calibration. And you can double check that then with other plots. What it turns out, what this graph here really clearly tells you is you have seasonal miscalibration. It only happens during certain periods that you have miscalibration, and during others it doesn't. You would never see this if you just look at the overall histogram. So I think that is a quite nice feature that you can get here additionally from this test process over time. You know under which conditions do I gain evidence against my null. Second example here, different location. Here, let's focus on the 24-hour wind speed forecast. So we're on the bottom here. So this pit histogram is relatively flat. I mean, it's not perfect, but you cannot say it has a clear bias or anything. When you look at the e-value here, you see at the end of the period, we would not reject calibration. But it has a huge spike, like this is 10 to the 7. So we have a p-value of 10 to the minus 7 against calibration. Now, what has happened here when you look at the data up until 2012, before and after, is you always have forecast bias. but it's time varying, and the bias up until half the time goes in one direction, and then the pit bias changes into the other direction, and that averages out over time. You don't see that at the end of the time period, but you can spot it very nicely here. Now, let me get to the last example here in Mannheim, 48-hour precipitation forecasts. You see we have a bit of a dispersion error here. And in this case, when you look here, you have a case where this dispersion error seems to be not humongously strong, consistent over time, and you steadily gain evidence that you do actually have this dispersion error. So we have some other graphics. I didn't want to introduce too many graphics, also to show how these types of miscalibration show up very nicely in not only from this process, but also from the construction of the e-values in the paper. But I skipped this here because then I would have first have to introduce how I define them. But I hope this gives you a bit of insight why I think it adds. Of course, we have a slightly lower power. We have to pay something. But we do know we have the type 1 error control that we oftentimes think we have, but we sometimes compromise. In this way, we have it guaranteed, and I think we can really see much more from the structure what is going on with calibration or with forecast. So to conclude, forecast evaluation is usually sequential, so I think that inference method should have this as a built-in feature. It should not be something where we do with multiple testing correction and so forth. Of course, we can do it, and it may be appropriate in some cases, but I think it's better to use methodology that adapts for that better, and I feel that going for valid sequential inference in this way does account for this very nicely and is very close to what we're doing oftentimes. As I said, for these comparisons, there is manifold extensions. Some are work in progress, some haven't been done yet. But a lot of things are possible there. As I said, calibration can nicely be monitored sequentially. There is, theoretically, there's quite a number of open questions. As I said, it's a very dynamic area at the moment. The betting I showed you for the forecast comparison of binary predictions. So far, that's mainly heuristic, and it works. But of course, there could be more principled approaches. In different work that doesn't necessarily target forecast comparison, it turns out that if you use, for the betting, you use algorithms from online convex optimization, you get asymptotic power guarantees, which is quite nice. But here, it doesn't apply, unfortunately, because the setting is slightly different. But I think there's also on the theory side, there's quite a bit to dig and still to get out. One thing I should say, yes, we can treat higher lags, and we can treat them in a theoretically sound way. But I don't think also there, on the theory side, we're not at the end of the story. We do lose some power the higher the lag. This is the same for Diebold-Mariano tests, but it's slightly more pronounced for this methodology. But I also think it's not the end of the story. I think better combination formula are still possible. Yes, and I think this is where I want to close. Let me give you some references, should you be interested. I don't know if you can read them, but I guess the slides will probably be available, and that's what I have them here for. So thank you very much.
Thanks a lot, Johanna, for this nice introduction to this dynamic area of research on dynamic forecast evaluation. We have time for questions in the room. Yes, Kajal? So.
I have two quick questions. And given the fact that it's a huge system you develop, you may have an answer to this. First is that the confidence intervals that you plotted, do they take care of the serial correlation in the data?
Yes.
Okay, like David's sequential test, it did actually, right? So I suppose it does, right?
Yes.
But your line was fixed, just not changing.
Careful, I was plotting the test martingale.
Right.
Yeah. So this is like plotting 1 over a p-value. So there we have a fixed rejection threshold over time. There is, I didn't mention this in the talk because it would just, I tried to not be confusing. there's a whole, let's say, the counterpart of doing this in terms of confidence sequences, where you really see a confidence sequence where you say your parameter lies within these bounds with a certain probability. That can be done with the same methodology. It's just the same as inverting usual tests to confidence intervals. And then, of course, you don't have a fixed threshold, but you have as you have a confidence interval for one time point, you get a confidence sequence for each time point.
Right, that should be changing, presumably.
That will change, yes.
Over. The second question is the quadratic probability score that you're using as a measure metric. I'm coming from economic standpoint, where events that we analyze are rare events. Like the probability of the occurrence is 1%, 2%, 3%, okay? In those cases, your quadratic probability score doesn't really capture those small events, okay? Because you'll get a high rate, QPS, no matter what, 97%. So in those, what is the experience? Does your procedure would handle really rare, uncommon events?
Well, let me answer this in two ways. So the score you choose in the procedure is up to you. There's no need to choose the Breyer score. You can choose a different proper scoring rule if you think that's better for your application. So that's definitely not a limitation. Clearly, if you have events that occur very rarely, you can put in any score you like, but as I said, this area is still very much developing. I'm not 100% sure, but it always holds for rare events, how well you can capture differences in forecast performance. I think the methodology per se doesn't speak against it. It's whether you can define a target measure that you want to test in expectation that captures your problem well. If you can give me target quantity where you say, this is below a certain threshold if my extremes are captured well. In expectation, this has to be below a certain threshold if my extremes are predicted well. If you give me that statistic, then you can apply this method, right? But whether such a statistic is designable, I don't know. Yeah, do you yeah?
I think you have some results for tornado prediction, for example, right? Essentially very rare, and very often these things do not capture it, That's my experience.
Yes.
In that sense, I said, because of a system, you can accommodate that possibly.
Yeah, you can accommodate it, but yeah, I do agree. It's a very interesting question. Yeah.
Thanks very much for a very good talk. You started with this point about the, I'll say, practitioners, or I don't know, our students kind of cheating, not on purpose, right? But here, then you have the issue of the starting point, because as you say, it goes up and down, right? But you have this threshold. So if you had started later to accumulate your evidence, it would not be conclusive, right? So from a practitioner point of view, then we have to be a bit careful how people are going to choose their starting point, because they could try to make things inconclusive just by starting later and in the right period, right?
Well, I think the problem doesn't appear if your aim is really to reject your null. So in the forecast comparison thing, I don't think it matters, because if you start later, you have less time to gather evidence. So why would you start later? So that's fine. On the other hand, but this is a general problem with goodness of fit type of statistics, in the calibration part, of course. If you want to show there's no evidence against calibration and you test the null of it being calibrated, that has nothing to do with the methodology. That's in principle, we're posing the wrong null hypothesis. And that's the problem for all goodness of fit tests. We haven't solved that problem, no.
We have another question here.
Thanks for the great talk. So my first question is, since the entire testing framework relies on the supermartingale structure, so I assume that it will hold for irregularly spaced series and also continuous time domains, right?
Sorry, say the last two things again. I acoustically didn't.
Irregularly spaced time series and also when the time domain is continuous?
Yes.
Okay. Yeah. And I am just curious, since you have already discovered the supermartingale structure, do you have any in-distribution convergence results?
In-distribution convergence results of what exactly?
I mean, the test statistics can be written as a function of t. So for every time point t, you can have a cumulative distribution function ft. So
No, I don't think there are any. I don't see why we would look at this.
I think more from a theoretical point of view. Like, for example, we have Brownian motion kind of thing as limiting distribution. So I'm just curious if you have explored this direction.
I certainly haven't looked at it. I cannot tell you 100% that it's not out there somewhere in the literature, that someone hasn't looked at it. I think it's not so prominent here because the testing really goes via a condition on expectations, which of course simplifies things a lot because you don't need to know distribution, right? You need conditions on expectations. But yeah, so I'm not sure if it's not out there. I have not worked on it, no.
Okay, thank you.
So we have time for one additional question. Yes, Tals.
So when I see this sequence of e-values, I can't help but think, is there a way to use this to test for things like structural breaks or regime switching? And if so, would it give similar types of advantages that it would work in a non-fixed T type world?
Yep, it's not by me. Aditya Ramdas, his group has used e-values for change point detection. There is, on his website, you certainly find it also on the, he's one of the conference organizers of the conference I mentioned, and I know that his group has worked on change point detection with this framework.
Okay, so now I think it's time to thanks again, Johanna, for this great presentation. Thanks a lot.